Hello everyone, I am back again. Good afternoon everyone. I'm really sorry there was some network issue, so we had to restart the class. Please share this video with your friends. Ask them to join back again. We are going to start with the questions now. There was some network error, therefore we had to restart the class. Quickly join, share this video with your friends, ask them to join again. We are going to continue with the questions now. If you haven't liked this video, yet, please like this video. Am I audible, everyone? If I'm audible, please write yes in the comments. Am I clearly audible? Is everything okay? Okay, so we will begin with the questions again. Since we got disconnected due to some network problem, we are going to begin from the very beginning. Quickly, everyone connect. Okay, so the very first question for today is, the Maxwell distribution speeds of a gas at 300 Kelvin is given below. The molar mass of this gas in gram per mole is. Okay, so we have this curve which has been given over here. It is a distribution curve for a particular gas, and we have been given this curve at a particular temperature which is 300 Kelvin. Okay. Hello, Mohit. Please quickly ask your friends to connect. We are going to start with the questions again. So here we have been given this distribution curve at 300 Kelvin. Okay, so we have to determine the molar mass of this gas. So as I was explaining earlier, so if we have a distribution curve where in the curve, wherever the peak is maximum, that speed is actually the most probable speed or the most probable velocity. Now, if we shift a little from the peak where it is highest, then we get the average velocity. And if we shift further away, then we get the root mean square velocity. So there are three kinds of velocities. One is the most probable velocity, then is the average velocity, and the third one is the root mean square velocity. So in the previous question, the peak is highest over here. Okay, so this is the most probable velocity. So how can we calculate the molar mass for this gas at 300 Kelvin with most probable velocity as 500? So the most probable velocity, the formula that we have for the most probable velocity is under root of 2RT upon M, where R is the gas constant, T is the temperature, and M is the molar mass. Now, upon substituting all of these values, we can easily calculate the molar mass for this. 500 is the most probable velocity, then under root of 2 into R. The value of R has already been given in the question, 8.3. We will substitute that. Temperature has already been given 300 Kelvin. We will substitute that and we can easily calculate M from here. All right. I don't think there should be any problems regarding this. This was a very easy question. Now I will move on to the next question. This is the solution. The final answer that you will get is 19.9. Okay. Now, The next question is, according to the kinetic theory of gases, the ratio of root mean square velocity of molecular oxygen and molecular hydrogen at 300 Kelvin is. Now, we know that the formula for root mean square velocity, earlier we did what? Most probable velocity. In this question, what we have been given? We have been given the root mean square velocity. So the formula for root mean square velocity is this. URMS is equal to under root of 3RT by M. Okay. So if we have to calculate the ratio, how can we do that? How can we calculate the ratio? We will write under root of 3RT, the molar mass of O2, 32, and its ratio with that of the most probable, the root mean square velocity of H2. So 3RT upon 2, that is the molar mass of H2. Upon simplifying this, we will finally get 1:2, 1:4. Okay, so our answer from here will come out to be the C option. All right. I hope all of you have been able to understand this. Now we will move on to the next question. Now over here. So in this question, the unit of the constant A in van der Waals gas equation of state of a real gas can be expressed as. So, as I had explained earlier, only a pressure term can be added to another pressure term. We know that the equation for real gas is this. This is the equation for real gas. P plus AN square by V square into V minus NB equals nRT. This is the equation for real gas. Now, we have to find out the unit for A. So how can we do that? We know that P is pressure here, and only a pressure term, another pressure term can be added to a pressure term. So AN square by V square should be equals to Pascal. It must be equals to Pascal. Now, we will substitute the unit for these in this equation. A will come as it is since we have to determine its unit. Then in place of N, we will write mole. So it will become mole square, and in denominator, in place of volume, we will write meter cube, and the square will remain as it is. Now, to calculate the unit of A from here, we will have Pascal into meter raised to the power 6 into mole raised to the power -2. Now, one important thing to remember here is that Pascal meter cube can also be written as joule. So we will substitute the value of Pascal meter cube with joule, and then we will get these two units for A. So our correct answer would be option A and option D. Did you all get it? I hope there is no problem regarding this. Now, we will move on to the next question. So, the behavior of Cl2 is closest to ideal gas behavior at. The behavior of Cl2 is closest to ideal gas behavior at which of these? Quickly write in the comments and let me know which of these should be the closest to ideal behavior for Cl2. Let me know in the comments what do you think should be the answer for this. So since we know that for an ideal gas, the conditions are high temperature and low pressure. We are well aware that an ideal gas is always considered at HTLP. We can write it as HTLP. It is high temperature and low pressure. So which of these has the highest temperature? 200 degrees Celsius is high temperature and 0.5 atm is very low pressure. Yes, Makran, very good. C is the correct answer to this question. So the behavior of Cl2 is closest to ideal gas behavior at 200 degrees Celsius and 0.5 atm. Okay, now we'll move on to the next question. This was a very easy one. Quickly subscribe to our channel if you haven't done that already. Please like this video and share it with your friends. Also, you can hit the bell icon so that you will be notified whenever we will come up with new videos. Now, moving to the next question. Assuming ideal gas behavior, the density of O2 gas at 300 Kelvin and 1 atm is, we have to find out. So if we assume ideal gas behavior, we have to determine the density of O2 at 300 Kelvin and 1 atm pressure. Okay, so this question is very easy. See, since they have mentioned about ideal gas behavior, what do we know? We know that the equation for ideal gas is PV equals nRT. Equation for ideal gas is PV equals nRT. So from here, what we can write, PV equals, N is the number of moles. We know that we can write number of moles as, given weight upon molecular weight into R into T. All right. Now we will take V also on the right hand side and we will write it as given weight upon volume into RT upon M. Okay, so from here we will get, we know that given weight upon, given mass upon volume is equals to density. It is equals to density D and it will become RT by M. Okay, so from here, what we have to calculate? We have to calculate the density of O2. So we can easily calculate the density of O2 from here. After substituting all of these values, we will get equation for D as Pm upon RT. What do we have? The value of pressure as, the value of pressure we have been given as 1 atm into mass of O2 will be taken here. Okay, 32. The value of R we have been given in the question. In terms of atm, you have to be very careful what value of, if suppose the value of R has not been given in the question, you will have to be very, very careful about what should be the value of R. So since here pressure is of atm, we will take the value of R also in terms of atm. And the temperature is 300 Kelvin. Quickly solve this and tell me what should be the answer. Quickly solve it and let me know the answer. So the answer from here should come out to be 1.3 after solving it. Your delta is same as D or density. Okay, Makran, very good. Told the correct answer, very nice. Okay, so this question and the final answer will come out to be 1.3. This is the final answer to this question. Okay, now we will move on to the next question. Okay, here the question says, H2 and N2 gas. We have what? H2 and N2 gas. The density of this mixture is, we are also given the density of this mixture. The density of this mixture is 0.2 gram per liter at 300 Kelvin and 1 atm. Now, assuming that both the gases behave ideally, the mole fraction of N2 in the vessel is. So, in this question, we have been given two gases, H2 and N2. Okay, we have been given the density of the mixture at 300 Kelvin and 1 atm pressure. Now we have to assume that both of these gases behave ideally. What do we have to calculate? We have to find out the mole fraction of N2. How can we do this question? We just now came across this equation in the previous question, which was dRT equals Tm. We had just derived this equation in the previous question. Now here, since it is a mixture of gas, here D is density, R is the gas constant, T is temperature, P stands for pressure, and M is actually the effective molar mass. Okay, M is what? M is actually the effective molar mass. So what is the formula for effective molar mass? Suppose we have two gases here. The formula for effective molar mass is going to be N1M1 plus N2M2 upon N1 plus N2. This is N1 is the number of moles of gas 1, M1 is the molar mass of gas 1 plus number of moles of gas 2, molar mass of gas 2 divided by the total number of moles. This is the formula for effective molar mass. Now, if I simplify it, if I take, okay, let me take another pen to explain it better. So, if I take it with this, and if I take it with this separately, I can also write it as Chi1 M1 plus Chi2 M2. Now this is the mole fraction. This is what? This is the mole fraction. Chi1 and Chi2 are the mole fraction of the two gases. So now here, if I put the values, these values, if I put here, what do I get? What will I get? We have been given the density of the mixture in the question itself, which is 0.2 into, we have been given the value of R here. Okay? So I will substitute the value of R as 0.082 into the value of temperature has also been given here, which is equals to 300. Now it will be equals to, the pressure is 1 atm into this M effective. Okay, into M effective. So if we solve it, how can we solve it? We can solve it as 0.2 into 0.082 into 300 is equals to, now if I substitute the value of M effective, I can write it as mole fraction of N2 into the molar mass of N2 plus the mole fraction of H2 into the molar mass of H2. Now, how do I solve this side? This side will remain the same. You just simply have to solve it. Now here, since we have to determine the mole fraction of N2, the term of mole fraction of N2 will remain as it is. Okay. But this mole fraction of H2, we will convert it in terms of mole fraction of N2. So I can write it as 1 minus mole fraction of N2 into mass of H2. I will erase it so that you can see the question better. Okay, so this is how we have done it. We will simply substitute the values of the molar mass here and we can easily determine the value of the mole fraction of N2. Okay. Quickly solve it and let me know the answer in the comments. What should be the answer? What should be the final mole fraction? Please let me know the answer to this in the comments. What should be the final mole fraction? What should be the mole fraction here? You can use your calculators, take out your calculators and try to solve it. Zero 0.082. So the left hand side would come out to be 4.92. It is chi N2 into molar mass of N2 is 28, and we can write it as, we know that the molar mass of H2, we will open up the brackets here. The molar mass of H2 is 2 minus 2 into mole fraction of N2. On simplifying it, we will take 2 to this side, it will become 2.92 is equals to, this will get subtracted from this, so it will become 26 chi N2. So finally the mole fraction will come out to be 2.92 divided by 26. Okay. So the mole fraction will come out to be 0.11. I hope this question is clear to everyone. There should be no problems. Now we will move on to the next question. So moving on, this question here says the relationship between the van der Waals B coefficient of N2 and O2 is. What will be the relationship between the van der Waals constant B of N2 and O2? So we know that the van der Waals constant B is actually 4 into the molecular volume. See, we know that B represents 4 into the molecular volume per mole. So from N2 and O2, which of these has higher molecular volume? We know that N2 has higher molecular volume. Therefore, the value of B for N2 is going to be higher. Therefore, BN2 will be greater than BO2. This is the correct answer. Okay, this was an easy question. You just have to know how B is related to molecular volume, and you can calculate and compare the value of B for different gases. Now moving on to the next question. From the kinetic theory of gases, the ratio of most probable speed to root mean square speed is. We have to calculate from the kinetic theory of gases the ratio of most probable speed to the root mean square speed. In the previous questions, we have already done the formula. We have already seen the formulas for the most probable speed as well as the root mean square speed. We know that U most probable to its ratio with U root mean square is equals to, so U most probable. We know that the formula for U most probable is under root 2 RT by M. Okay, under root 2 RT by M. Its ratio will be U RMS under root 3 RT by M. On simplifying it, we know that we will easily get root 2 is to root 3. This one was a very easy question. There should not be any problems in this question. We simply had to take out the ratio of the most probable speed to the root mean square speed. We will just equate their formulas and we will get root 2 versus root 3. Yes, Makran, very good, correct. B is the correct answer. Now moving on to the next question. Now this question says a 10-liter flask containing this question is important. A 10-liter flask containing 10.8 gram of N2O5 is heated at, what is the quantity of N2O5? It is 10.8 grams. It is heated to 373 Kelvin, which leads to its decomposition according to the equation. We have been given the equation of decomposition of N2O5. If the final pressure in the flask is 0.5 atm, what is the final pressure? It is 0.5 atm. Then the partial pressure of O2 in atm is, we have to calculate what? We have to calculate the partial pressure of O2. Now, in this question, first of all, we will begin by calculating the number of moles of N2O5 from the given amount. Okay, so we will begin by calculating the moles of N2O5. The moles of N2O5 will be, what is the given mass? 10.8. What is the molar mass? What is the molar mass of N2O5? The molar mass of N2O5 will come out to be 108. So we can calculate the number of moles here for N2O5 by dividing the given mass with the molar mass. So we will get the number of moles as 0.1. So we got 0.1 moles. Now, here we have been given pressure. Okay, we have been given final pressure, temperature, and we also have volume. So we can also easily calculate the total number of moles. So what is the equation? What is the ideal gas equation? We know that the ideal gas equation is PV equals nRT. From this equation, we can easily calculate the total number of moles. So N will come out to be PV upon RT. Okay, it will come out to be PV by RT. We know that the value of pressure here is 0.5. The volume has been given as 10 liter. The value of gas constant has already been given in the question. We will just substitute the value. It is 0.0821 into the temperature has been given as 373 Kelvin. Now quickly solve this value. Quickly solve the total number of moles and tell me the value in the comments.